Hello everyone. Please say yes if you can hear me. Good. Perfect. Please say yes if you can see my screen. It says rendering pipeline 4 and it has a dragon. Perfect. Okay. So we will have the same type of lecture today from the previous one. I will have I think 2 or even 3 pauses for questions, and you can raise your hand and we can like open the audio, and that's good. And we also have TAs on the lecture, and we might also check the chat for some of those questions, right? But remember, questions will be either raising your hand, or if we can't answer your question on time, you can post it on Piazza. Okay, so today we will hopefully finally end with the rendering pipeline, the very last part of rendering pipeline. And let me just move my windows here. So we have 61 participants, which is good. Okay, give me a second because I have notifications and I need to, okay, so let's start. So the learning goals for today is we'll check the fragments versus pixels, basically an explanation of the difference between fragments and pixels. This is very relevant because usually I think fragments is something that it can be confusing for people that is outside computer graphics. And I've checked, and we have 10 books already, right, on our list of textbooks, and there is no book in which you can see like a truly good and formal definition of fragments, right? In some of those, actually, I think there were definitions on only 3 of those books, and the majority they just never mentioned, because this is kind of like a concept that everybody should know already. What is that? And yeah, it's never defined. So we will define it today, and we'll see the per-fragment operation stage. You will see that it's not a single stage, but like a lot of steps. And if we have time, we will also cover the beginning of coordinate systems today. I don't think we will have time for that, but yeah, that depends on the number of questions you had. Okay, so let's see the per-fragment operations. So this is where we left our previous lecture, right? So it was like a long way up to the end of this stage, or the end of the pipeline. So this is very relevant. The per-fragment operation is basically when we finally convert fragments into pixels, right? And as already said, a pixel is unique, is the very end of the pipeline, and fragments are this very weird stuff that I will explain right now. Okay, so let's consider this. Let's consider a couple of triangles, T1 and T2, that are visible from a perspective camera, okay? And let's imagine that this camera will render an image of 10 by 10 pixels, right? So this is our image, 10 by 10 pixels, which, by the way, it has its origin on the upper left corner. So this is 0, 0. Again, this might sound for you weird, like why the origin is up there. Don't worry, you will eventually understand. But this is just a common thing in computer graphics. Okay, so having these triangles, the triangle vertices, right? So in this case, A, B, and C for T1, D, E, and F for T2, they have information, right? We know that. They have information, they have position, normals, they can have texture coordinates, they can have, of course, they have their color, right? And they can have also uniform variables or varying variables, right? We are sending information from our application. We are sending information to the vertex shader and to the fragment shader. We know those variables that we can use those variables, right? So they contain information. So we know that these vertices are transformed to screen coordinates by the vertex shader, right? This is by using different transformation matrices. And this is like projecting these triangles into the screen. So let's assume that we want to paint the pixel on the screen coordinates 6, 5, which is this pixel right here, right? And so it's by saying that we have these triangles projected into the screen is like having a ray that is launched from the camera and is passing through that pixel and going through the triangles, right? And we can see that there is a portion of each triangle that is basically or partially or fully overlapping that pixel. In this case, they're fully overlapping that pixel, but it can also be partial, right? Again, this is not what actually happens on WebGL or OpenGL, right? This is just for visualization purposes. We are not firing rays. We will fire rays with ray tracing. That is totally different rendering paradigm. But in this case, it's just for visualization purposes, right? What we know is that we will transform these vertices, and in the end, they will have a screen version. We will have a screen version of these vertices on the camera perspective coordinates. So let's call these points, these portions of these triangles, let's call them F1 and F2. So F1 is the portion of the triangle that is basically colliding or is in the same position on screen coordinates than the pixel from T1, and F2 is that portion of the triangle, in this case of T2, that is exactly in the same position in screen coordinates than the pixel, right? And these points have interpolated values from their triangle vertices, right? Again, they have position, normal, color, they can have texture coordinates, varying variables, uniform variables, whatever we send to the vertex coordinate, sorry, to the vertex shader, but their values will be interpolated, right? We remember that. So for example, in the case of the color, this fragment here, or the color that we can see in this portion of the triangle, is not exactly the same as this blue here, or this blue here, or this blue here, because in the end it's an interpolation of those three colors, right? Same happens here, right? These vertices colors, these vertices are red, and this is yellow, and this is kind of orange because it has like a interpolated value, right? So if we need to compute the pixel, the color of the pixel, right? That depends, that computation, it will depend on the information we can get from those points, F1 and F2, right? Because those are the points in space that are basically exactly in the same position that the pixel. So all the information contained on each of those points or each of those portions, combined with the location of the pixel itself, is what we call a fragment, okay? So F1 and F2 are fragments, and they're in some sense like candidate pixels, okay? They're not pixels yet, right? Because the pixel is the very end of the pipeline. So they're not pixels yet, because they can be discarded or combined exactly on these fragment operations, right? So these fragments operations will be like a set of tests, a set of operations that we will perform to either combine or discard fragments in order to compute the final color of the pixel, okay? So again, I will repeat. The fragment is the set of information that is contained on each of these portions with also the coordinate of the pixel. So to discard a fragment, we can use different criteria. The most common is the depth, for example. That is the distance from the fragment to the camera. So as we can see here, this is in 3D, right? The triangle T2 is closer to the camera than T1, right? Which means that the depth value from F2 is different than obviously the depth value of the F1, and F2 is closer to the camera, right? So what do you think? What do you think about F1? Should we discard the fragment F1 by the depth? So say yes or no on the chat. What do you think? Depends on the alpha value. Hey, yes, Nam, very good. Okay, but many people is saying yes. So yes, it seems that based on the depth information, we should discard F1, right? And keep the color value of F2, right? At least with this information that we have. However, num is saying that it also could depend on its color, right? So let's assume that the color of F2, the GLF frag color, remember that we have that variable, that the variable that is basically the output variable from the fragment color. Let's assume that that color is this one, okay? So the vec4 for that variable contains RGB, basically red, green, and blue for color, and it has a fourth value that is called the alpha value or the alpha channel, and it means that the fragment is not, well, in this case, because this value is less than 1, it means that this triangle or this fragment is not entirely opaque. So if the value of the alpha channel is 1, it means that the object is totally opaque, which means that it will block 100% of the light that is behind its position, right? So in this case, for example, it's 0.7, it means that it will let 30% of the light passing through that object, okay? If it says 0, for example, it means that it's 100% transparent, right? It will let everything pass. So here we can see, the interpolated color values for each triangle, and we can see that T2 is actually transparent, right? So if this is the value, let's imagine for now that 0.7 as alpha value is also in all the vertices from the triangle, right? Because this could be an interpolated value, right? Let's assume that the entire triangle T2 is basically 0.7 in alpha value, so it means that it's transparent, right? So what do you think? What can we do now? So if it's transparent, can we discard F1, or can we keep F1, or what do you think? Merge, multiply. Yes, so somehow we need combine these values, right? So in this case, yes, we can't discard F1, right? So we need to compute a new color that will be a combination of those two colors, right? So we'll need to interpolate those values using the alpha channel values. I will not get in deep right now, how do we actually blend these values, because there are many different ways to compute two colors, right? In the end, for example, colors are like vector, right? If a color is RGB, right? It's like having a position on R, G, and B basis vectors, right? So it's like having a position in 3D space. So one way to interpolate between two colors, for example, is just having a position that is basically in at a certain position between those, right? So you can, for example, multiply one color times 0.7 and the other color times 0.3, and you could have something that is basically in the middle, right? Yeah, so you can treat them as vectors, but you can use very different ways to combine. This is basically like having Photoshop, for example. If you have two images in Photoshop and you can combine those images, you can perform different ways of combining, right? You can have a screen filter, you can multiply the values, you can add the values, whatever, right? And depending on that, on the function that you use, is the type of effect that you will obtain, right? Okay, so, but in the end, we need to combine them, and this is what is called blending, okay? So we will blend these two fragments to compute the final color of that pixel. So these two fragments before they were candidates to become pixel, and in the end, they were not discarded, they will combine, and then we have a final color, which is this one, right? So if we do the same for every pixel on the image, we end up with the final image, right? And yes, okay, so with this very short explanation, I hope that we can finally understand the difference between pixels and fragments. So again, the pixel is the final output of the pipeline, and it is unique, right? And a fragment is a set of interpolated values that represents a small portion of a triangle, and that it could be candidate to become a pixel, right? And we use that information to either discard the fragments or combine them to create the pixel. So let's take a moment for a small break and questions. So anyone has questions regarding these concepts? You can raise your hand. Okay. Yes. Now we can hear you.
Hello.
Oh, no,
so
sorry.
my understanding
Sorry.
of
I was not hearing you. I'm sorry. My volume was... Yes. Okay. Now I can hear you. Sorry.
all right. So the triangles that we're rendering, I know those are just simple examples, but I guess at the final step we have millions of triangles to render. So are the fragments based on the super small triangles, or where you're trying to just show big surfaces being rendered, and fragments are independent of how small the triangles are?
No. Yeah. So in the end, if the geometry that you have at that point of the pipeline, remember that the geometry is not what you have in your application stage, right? So you can have maybe 1 million triangles on a 3D model, and eventually previous stages of the pipeline, you can discard a lot of triangles, right? You can actually create new triangles by subdividing, by tessellating the triangles, or you can discard. So from the amount of triangles that are in the end left in your OpenGL or in your pipeline, yes, fragments are basically computed for every triangle on your geometry. So if you have 1 million triangles, you will need to compute all the fragments for the million triangles that you have. Yeah.
I see.
Yeah. Okay. Then we have give me a second. Mute. Yeah. Sorry.
Okay.
Yeah.
Can you hear me?
Yes, I can hear you.
Okay. My question is the background color always white?
Is what? Sorry.
The background color always white?
Oh no, very good, very good question. In my slides, it's always white, just because yes, I decided. But no, you can decide the color of the background. That is one of the very first things that you can do on WebGL when you define either WebGL or OpenGL or 3.js, whatever. But yeah, but basically you define the color of your background, and you can also set the color of the background with a texture. So for example, you can define there are certain type of textures that are like panoramic type of textures that basically you have like a front, top, bottom, left portions of those textures, and you can use those, for example, to fake reflections, right? So in that case, your background could be not as a single color, but like I don't know, like a background from Vancouver, and you can like render stuff that it seems that is like reflecting Vancouver. But yeah, no, it's not always white. You can define whatever you want, and of course, if you have, for example, a triangle that it has, or a fragment that it has a alpha value that is less than 1, so it's transparent, it also needs to blend with the background, right? So I only said that we were computing the blending between those two triangles, right? Because in the end, F1 is totally opaque, which means that I don't need to use the background. But if T1 would also be transparent, it means that I need to blend between those two fragments and the color of the background, right? Maybe your questions was kind of in that sense.
Okay. Right.
Good. Okay, so
Thanks.
anyone else? Any other question? Oh, someone is asking on the chat. So alpha is range for what about B? Yes, that is a good question. Well, depending on which like each technology or software that you're using, some libraries or some systems, they use for RGB and alpha, they use values from 0 to 255, and some others use values from 0 to 1. So in this case, for example, OpenGL uses from 0 to 1, and that's it. So you can't go over 1. So basically, yeah, red, green, and blue are constrained from 0 to 1. Yeah. Okay, so can I continue? Say yes if you don't have... Oh, sorry. Yes, you have a question. Mark.
Okay, yeah, I'm just wondering, is the method used to combine fragments in software quite complicated, or just wondering?
You mean the blending? Do you mean the
Got muted there. Sorry. Yeah. Yes.
it can be very complicated. Again, it depends of what you want. So it can be something super simple as just multiplying the values, or you can use like a super sophisticated function because you want to, I don't know, take one of the colors of the fragment to obscure something on yeah behind. Yeah. So yeah, basically you could do whatever filter you can find on Photoshop or GIMP or something like that. Yeah.
Sorry, I have a question.
Yes.
So do we define a shape for a fragment, like a square or a circle, or it's just a set and we don't really talk about the shape of the fragment?
Okay, sorry. If I let me see if I understand the question. Your question is if the fragment has a shape?
Yeah.
Okay. No, they don't have a shape. I am personally, every time I show fragments on my slides, I draw the shapes or I represent the shapes as a circle, just to not confuse people from fragments to pixels, right? So pixel, I always draw pixels as the square because a pixel is a square, and the fragment as a circle because, but they don't have a shape. In the end, the fragment is just a position in space that contains interpolated information, right, from that triangle in particular. But yeah, they don't have a shape per se. Yeah, good question actually.
Okay. So it's kind of like a point and.
It's a point. Yes, exactly.
Okay, thank you.
Yeah, and you will see eventually when we talk when we will cover we will have actually I think an entire lecture on rasterization, and on when we talk about rasterization you will see that there is actually something called aliasing and anti-aliasing, that is basically if you rasterize, if you compute the fragments only using the middle of the pixel, usually you have like ugly images because if you have like the borders of your image will be like very jaggy because you have only discrete colors on your pixels. But yeah, you will see later that we usually compute the fragments not in a single position of the pixel but with different sampling, different positions in the same pixel to actually like compute more beautiful images when you have borders. But yeah, we will cover that. William is also raising hand. So, oh, sorry. Yes, William, we can hear you.
Yeah, I just want to check my understanding here. So the vertex shader outputs still 3D coordinates in terms of the camera perspective. Now.
Yes.
I read it's some between like -1 and 1. They normalize it, but so when rasterization process kicks in and creates these fragments for each triangle, it's basically mapping that 3D coordinate into 2D more or less pixel coordinates. But the difference between fragments and pixels is that there could be many of them corresponding to the same 2D pixel coordinate. Is that it? Each with its own color and other attributes.
Okay, almost. The thing is, yeah, almost yes. The thing is, fragments are not only 2D. So fragments are still information in 3D because you have depth. So the fragments, the position of the fragments, is already transformed in the camera or in the screen coordinates. So as you said, it's basically from 0 to 1. Well, I will explain that later, but yeah, you have a 2D component, but you also have depth. So they are actually 3D. It's 3D information. It's only until the very last part of the pipeline when you finally define pixels where is 2D at the end, right?
Perfect. Thank you.
Yeah. Okay. So I think no one else is raising hands. Yeah, okay, so let's continue. Good questions, by the way. Yeah, good questions. And sorry, by the way, I uploaded this the PDF on the webpage as I promised. I'm trying to do that before every lecture. But I will. But the one that I uploaded is like a clean version, so I will add more notes. So I will either replace the one that I'm already uploaded, or I will probably create a new version with more notes, because yeah, I'm trying to also like think on notes depending on your questions. Okay, so great. So that was conceptually what we do on this stage of fragments operations, right? So as I said, the fragment operations is a set of operations or a set of tests that we perform to either discard or combine these fragments to eventually compute the final color of the pixel. The thing is that this is not a single stage. This stage here is actually a pipeline in itself. So let's now review the pipeline of per-fragments operations. So it has 6 operations, but I promise this will be the very, very end of the pipeline. That is huge, okay? So we have 6 operations, and the first one is the pixel ownership test. So I will explain each one. Okay, so for the pixel ownership test, imagine you have something like this. You have, so this is my desk, and you have a window, an OpenGL window, in which you are rendering this bicephalous bunny, right? And eventually you just open another window, in this case, Google Chrome, right? So pixel ownership test, this test, what it checks is the ownership of the pixels from WebGL. So basically this is Windows every in 60 hertz, 60 hertz, basically 60 times per second. Windows is telling OpenGL which pixels are in its control, right? So in this case, for example, here. So if I have another window here, even though this is my entire window for OpenGL, right? And obviously this section here is seen by my camera and everything, right? Because Windows is telling, again, it's like refreshing every 60 times per second, it's telling OpenGL which pixels are from you and which pixels are not from you anymore. This portion of my screen from WebGL is now owned by Chrome, and this portion is only the portion that is owned by OpenGL, right? So this is an internal test from the pipeline. We cannot control this. This is totally controlled automatically, and is basically talking between either Windows or Apple or whatever system you have, or Unix or Linux or whatever, with WebGL, right? So this is totally automatic, and basically it determines, it will discard all the fragments on this area because, yeah, you don't need it anymore, right? You will not render them. That is the ownership test. Then we have the next, it's called the Scissor Test. This, at least for me, it's kind of weird because it's very similar to the ownership in the sense that there is a section of the screen that it will be like forbidden to render to. Okay, it will be like a valid area and an invalid area. The cool part of that is that this is user defined. So in this section here, the Scissor Test, you can literally code and send information to the Scissor Test saying, okay, this portion here, right, it will be defined as a valid area to render, and this portion will be invalid. The thing is, the reason I say that this is not very useful for me, at least, is that it is constrained to a rectangle area. Honestly, it's hard for me to give you an example of this. Maybe you can do some interesting effect, but I tried to come up with an idea, and I really don't see like a much value of this. Maybe, for example, I don't know, it could be used, for example, to maybe test just a portion of your WebGL window. Maybe you are computing a super sophisticated algorithm, and you, at that point, you want to discard everything but a single tiny window just to debug something. I don't know. But yeah, so basically what this is just a rectangle area that is user defined as the valid area. So basically every fragment that is on this area will be totally discarded and will not be rendered anymore. Okay, so the next one is the AlphaTest. So we already said something about it. It's very similar to the triangle example that we had, right? So depending on the color of the fragment, you can have an alpha value that if it's less than 1 and greater than 0, it means that you can combine colors from the fragments depending on its transparency. But here's another cool example. So in this case, this, so we have a palm tree here. This is a very common thing that you can see, for example, in video games. So this palm tree here has what it seems a lot of geometry, a lot of details, right? And one can think, oh my God, like those are a lot of triangles to compute, right? This will take forever. Well, it turns out that this is just a texture, right? But this texture it has some transparency or some like cooling effect, right? This is done by having different textures. Remember that the texture is also an information that you can send to the to OpenGL, right? Is one of the information that is actually traveling and going to the vertex shader and then traveling to the fragment shader. And yes, texture coordinates and texture values is one of the values that you have in your vertices and in your fragments after they're interpolated, right? So the diffuse color or the actual color of the texture is here, and you can have information of diffuse plus alpha values. So if that alpha, for example, in this case in particular, is equal to 0, it means that some of those fragments will be totally transparent, so they will completely discarded, right? And you can have this very nice effect that this geometry is way more complicated than it is, when in reality you have just a very low poly leaves, right? Instead of having a lot of geometry. And this is done by AlphaTest. So every time in video games, when you see like trees and plants and things like that, and sometimes you see like super complicated shapes, they're usually just textures with alpha value. This is also done, for example, with hair. So instead of having millions of hairs, you can have just like patches, planar patches in a character, and those patches have a texture that has basically, yes, an alpha value, right? Okay, then we have the Stencil Test. This is very cool, and this is similar to the Scissor Test in the sense of it's a user-defined way to define pixels that are valid to render and not, right? The thing is, this is not constrained to a rectangle. So in the Stencil Test, what you could do is you could save a boolean value in something that is called the stencil buffer. Every time you hear the word buffer, is what we were talking about. Buffers in rendering pipeline is basically a chunk of memory, right? Or a set of data that we save, and that we use that data, those buffers, we use those to transport data between stages on the pipeline, right? So the stencil buffer, what it does is it takes for every pixel on your image, it takes a value either 1 or 0 that tells the pipeline to discard or keep pixels. So I don't know if you know this this video game here. So say yes if you know this video game. Portal, yes, exactly. Yeah, I think everyone knows this, right? This is a very cool effect that you can see in Portal, right? That basically what you see here is basically like a window to another area on your scene, right? What is done here is basically is a trick that is created with the Stencil Test or with the Stencil buffer. So what happens here is that you can use this stencil buffer or this Stencil Test as a mask. So this portion right here, right? It's the triangles of this area on the scene, right? They could have, for example, a texture that tells you that this portion here will represent a different camera. So the entire scene is maybe rendered with camera 1, so you can have different cameras on the same scene, right? So this entire set of objects, for example, they are rendered with camera 1, and this portion here you can say to the Stencil Test, you can say, okay, the camera 1 can paint pixels on every single part except on this one. So it's like defining a mask, right? So camera 1 is forbidden to define pixels on this area, right? And you do the opposite for the camera for the second camera, right? So you have a second camera that has forbidden to paint on these other pixels except for this one, right? So basically what you do is you create your render with 2 passes. So So you have one pass for the camera one and one pass for the second camera, and you basically decide which portion of each camera you see depending on the stencil test. And you do that by sending information to the stencil buffer, usually with texture, for example, that will define these Boolean values to say, okay, I want these pixels for this camera and I want these pixels for the second camera. Yeah, so this is very, very, very cool example of the stencil test. Okay, so then we have the depth test. Again, we already discussed about this. So if you have a scene, right, with a lot of triangles, in this case, like millions of triangles, this model in particular has, I don't remember right now, but I think it has like 6 million triangles or something. It has hair and all those, a lot of things. But you have a lot of triangles, right? So for every triangle, you have a lot of fragments, and for every fragment, you have a depth value, okay? So depth values are also stored in a depth buffer. Again, buffers are like structures or chunks of memory in which we save information that we can use in the pipeline. And this is like this is how the depth map will look in the case of this image, right? So white is near, black is far, and this can be used for discard fragments. And if some of you are wondering if you could do or use depth also to create effects, for example, like fog, right? Because you're like, hey, yeah, so I have information, I have depth information, I can use also like that, right? Kind of like the inverted version of this, to have like the I don't know, buildings that are very far on my video games to be like faded using the fog effect. Yes, you could do that, but remember, these are the very last steps of the pipeline. Usually these per-fragment operations are either to combine color values that are already computed or discard fragments. So a fog effect would be typically done in the fragment shader, for example, right? So you can, at the fragment shader, you obtain position values, interpolated position values from your vertex shader. You have depth information of your fragments. You can modify the color of your fragments at the vertex shader, right? Not at this point. So this is, again, maybe you could use it, right, to modify the color, but usually is not for that. It is usually for discard fragments, depending on its depth. Okay, and at the very end we have the blending, right? So for each color of the fragment, each fragment, they can be either discarded or combined. And this is the very, very, very last, finally, the very last part of the pipeline. So the result of this blending operation, that again, it can be super easy as just multiplying the colors, or you can have like a super sophisticated function that you want. But yeah, but basically is the very, very last part. You discarded everything that it was possible to discard it. You kept everything that you wanted, and you just blend, either combine, multiply, or whatever. And the final output of blending is the actual final value for the pixel, right? So blending is the one that actually writes pixels, okay? Okay, good. So that is the per-fragment operations pipeline, okay? And that is the end of rendering pipeline. So we have another break for questions. So you can raise your hand if you want. Well, someone is asking, could you please explain the Scissor Test again? Yes, of course I can. Okay, so this Scissor Test, let me just go back. Yes, the Scissor Test. The Scissor Test is a user-defined stage. You can code the Scissor Test. There's a syntax in OpenGL in which you can send information to Scissor Test. What it's basically do is you define a rectangular area in your screen coordinates, from which you define which fragments are valid, or which pixels are valid to render and which are not valid, right? So actually the rectangle area is usually the area that you define as valid. Again, it is very hard for me to find a good example of this, because yeah, again, it's like a masking, right? So it seems very similar to the stencil test, The thing is, the stencil test allows you to define the mask in any shape you want, but in this case, it's exclusively in a rectangular area. So, is that, you understand? Yeah, it's good. Good. Okay. So someone is asking, could you explain the AlphaTest again? Sure. So the AlphaTest again is similar to what I explained with the triangles, right? So if so we have at this point we have fragments, right? And fragment has color values, and the color values have red, green, and blue, and alpha value, right? So the alpha value, remember, is the value that defines if the color or the fragment is opaque or transparent. If it's 1, it's totally opaque. If it's 0, it's totally transparent. If you have a value between 0 and 1, it means that you will probably blend the color with whatever object that is behind that or the background, okay? So in this case in particular, this application, the application of using AlphaTest for trees and things like this, what is happening is that the diffuse value of this image here, this texture of the tree leaf, it has values, it has alpha values of 0. That means that they are completely transparent. So once the pipeline is rendering these parts, those portions of the image, right, those fragments are getting information, getting its color information from this texture, they are basically totally transparent. So it gives the effect or the illusion that you have way more geometry than what you actually have. So, yeah. Is that clear? Okay. Very good question. Someone is asking, sorry, Ashley, do all these tests have to happen one after the other in this particular order, or it can happen simultaneously? As far as I know, it is sequential. This is a pipeline, and it is sequential. Yes, I mean, this technology changes a lot. Yeah, maybe they changed a week ago, and now some of these parts can be parallel. But as far as I know, no, it is not. It is a sequential order. They need to happen in this order. Someone is asking this. Does pixel ownership test use GPU while dragging the Chrome window crashes GPU? Okay, everything that we said about the rendering pipeline, beginning from the vertex shader, so every single stage is done in the GPU. So everything uses GPU. Yeah. Okay. So yeah, even obviously the pixel ownership. And the second question, will dragging the Chrome window crashes GPU? No, it doesn't crash because Windows is handling that. So Windows is all the time like checking the ownership of pixels all the time. And Windows is not only checking for WebGL. I mean, you can, if you have whatever, if you have PowerPoint and Photoshop in top one of the other or whatever, Windows is doing that already, right? Windows is defining which pixels of your screen or your monitor belong to your PowerPoint and which belong to your whatever, navigator or whatever, okay? So yeah, it doesn't crash. Windows is sending that information in real time to the GPU, to your rendering pipeline, and rendering pipeline is just taking that ownership and deciding which fragments are discarded. What is the difference between AlphaTest and alpha blending? Well, okay, AlphaTest is the stage in which you graph information from the alpha channel of your fragments and you decide if eventually you need to blend colors. Okay? Yeah, so the name of the stage is AlphaTest. The name of, yeah, but in which you can either blend or discard, right? Yeah, I mean, it's called test, right? Because, for example, if the value is 0, it's like failing the test. So it is defined as, yeah, maybe the name is not helping because AlphaTest sounds like if it was a Boolean test, right? Either you pass the test or not. So, but it's not exactly like that, right? So if it's 0, you fail the test, and basically that fragment will be discarded. If it's whatever value that is larger than 0, you in some sense are passing the alpha test, but you will be blended if the value is less than 1. If the value is larger than 1, right, you will keep the color if the depth test, if you pass depth test, right? Because remember that, yes, after the alpha test, you have the stencil test, and then you have the depth test, right? So every fragment is just waiting to see if it's discarded or not. Okay. Okay, so someone is asking, during rendering process, if you change the size of OpenGL window, does it cause problem? No, it usually doesn't cause problems. Yeah, this is handling very well. Either if you are either using OpenGL directly, or WebGL or T.js, yeah, whatever. That is something that you can actually control also. So usually when you define your canvas or your area for rendering, you define the size of your canvas, and you can define your canvas as fixed. So if, for example, if your canvas is, I don't know, 800 by 800 pixels, and you have the window, and you are resizing the windows, what it will happen is, if suddenly let's imagine that you are using WebGL and you're using Chrome, okay, and you take your Chrome window and you make it like smaller than 800 by 800. So what will happen is that Windows will tell OpenGL that only the portion that is visible on your Chrome window is able to render. So basically that will be part of the pixel ownership test. Okay, so if you resize and you are cropping your area of rendering, that will be handled by your pixel ownership test, and it will have no problem. But also you could code your OpenGL canvas or WebGL canvas to resize automatically, for example. So you can have a certain size, and you could have your Chrome window, and when you're resizing your Chrome window, you could make code to basically resize also your canvas, right? So if now your window is, I don't know, 400 by 400, now those are the pixels that you're rendering, 400 by 400. If the alpha value is 0, will it skip all the tests or just run through all the tests and showing nothing? Oh, that is a very good question. Actually, what happens on any test is that if fragment, so for example, this is the entire pipeline for fragment operations, right? So if a fragment is failing whatever test on this pipeline, it is immediately discarded and is not anymore on the next stages, right? So if something is failing on the ownership, for example, that information is just not computed anymore on the next stages. So yeah, it is same on the alpha. So if the value is exactly 0, from this point further, you will have absolutely no information from that fragment, because yeah, it is already discarded. Okay, someone wants to ask questions with audio. Someone wants to raise their hand? Okay, I think not. Okay, good. So we still have a little bit of time, but I think, okay, let me continue. So, okay, so yeah, so finally we finish with the rendering pipeline. Okay, so try to see if you can, this will be a nice exercise. Try to see this pipeline and try to see if you can explain each part of the pipeline. Okay, try to make questions to yourself, seeing the pipeline. If you can answer questions, for example, saying like, okay, where does the triangles are actually created? Where does the fragments are actually created? Or which stages are sending information to which other stages, or which or in which stages are you working only with vertices, in which stages are you already working with triangles, and yeah, basically the meaning of each of those stages. So It's like, yeah, try to do that like an exercise for you, because we'll obviously ask a lot of things about the rendering pipeline either on the midterms or the final exam. And I will we will post a quiz tomorrow probably, because I think, if I remember correctly, I think the last quiz that we had, it's still available. I think it will be available until tomorrow. So we will probably post the new quiz tomorrow at the end of the day. And so I will post a quiz regarding the entire pipeline, okay? And I will put the type of questions that you can find on a midterm, right? But for now, yeah, let's try to ask yourself, if you really understand the entire process of the pipeline, and if not, if you still have questions, please post it on on Piazza. And again, I will add a lot of comments. So again, this is like the clean version of this presentation. I will add comments once we finish this lecture. I will add comments, and I will add more slides, and I will probably maybe replace the actual file. Okay, and we've finished, because it's perfect. Yeah, we need to wrap up, because we always need to end up at 50. So the plan for today was also to cover coordinate systems, but this is very fast, so don't worry. We will cover on Wednesday. This is actually very fast, because we will actually start with coordinate systems, and we will start with linear transformations. Okay, so if there is no further questions, no final questions, I think we can end up here. Any other question? Someone? Nope. Okay, good. Thank you, everybody. Thank you so much.